In this lesson, we're going to be taking a look at reasoning in algebra and geometry. So part of this is going to be a review of algebraic properties, and then we're going to look at what their parallels look like in geometry if such one exists. When we go through and do what are called geometric proofs, which we will also explore a little today, we have to use these properties in order to justify certain steps, in order to put together a logical train of thought. So as you can see here to begin with on our algebraic properties, we do have quite a few of them, and we will go through these rather quickly. Our first one is the addition property of equality. So the way it reads is that if A equals B, then A plus C equals B plus C. In a more succinct way, whatever you add to one side of an equal sign, you have to add to the other, and it allows it to maintain that equality. Subtraction property of equality. If A equals B, then A minus C equals B minus C. Whatever you subtract from one side of an equal sign, you have to subtract from the other. Now we use these properties when we are solving equations. If I see addition and I need to get rid of it, I use subtraction to do so. And if I see subtraction and need to get rid of it, I use addition to do so. So they're balanced in that manner. Multiplication property of equality is similar. If A equals B, then A times C will equal B times C. And these ones are true for any values of A, B, and C. Division property of equality. If A equals B and C does not equal 0, then A divided by C equals B divided by C. Here we do have the extra little piece that C cannot be 0, because in mathematics you cannot divide by 0 and maintain any usable number. Okay. Our reflexive property of equality says that A equals A. And hopefully you realize that that is quite obvious, that any item is equal to itself. So if I have 5, I can use 5 in any way, shape, and form. Okay. Symmetric property of equality. If A equals B, then B equals A. And this one might seem just as obvious, but some people have trouble using the equal sign to go both directions. They know that the number 5 is the number 5, and that 1 plus 4 equals 5. But sometimes we need to break it back down that instead of using a 5, I need to actually have that 1 plus 4. And we'll see this more as we move out of geometry into Algebra 2, pre-calculus, and calculus. Transitive property of equality says that if A equals B and B equals C, then A simply equals C. So I can skip over that middle piece and go directly from the opposite ends. Our substitution property says that if A equals B, then B can be used. It can be used any place that A was present in an expression or an equation. Okay, so we can make that simple substitution, whether it be a single item or an entire expression in its place. Our last one here, the division property of equality, tells us that if we have A times B plus C, then that is going to be the same as A times B plus A times C. Now we can also add into this one extra little piece, that if we have A times B minus C, then we would get A times B minus A times C. So we can use that one both ways. And again, remembering our symmetric property, that equal sign works both ways. If I have an item that's commonly distributed across a set, I can factor it out and still have an equivalent expression. Okay, so these 9 properties should have been used back in Algebra 1 when you were first learning how to solve equations. Might not have had formal names for them, but these ones are present. Okay, so what we do when we are solving equations is we employ these in order to get from a very complicated equation to a simple item. And let's take a look at how that works in conjunction with a little bit of geometry. So here, if angles AOM and MOC are a linear pair, we're going to solve for the value of x. Okay, so let's start out by talking about what does it mean to be a linear pair. According to our postulates and theorems, more specifically postulate 1.9, we know that if we have a linear pair, that equates out to the angles being supplementary. Okay? So what does it mean then for angles to be supplementary? That would mean that the measure of angle AOM plus the measure of angle MOC would have to equal 180 degrees. Now, using substitution, the measure of angle AOM is simply 2x plus 30. The measure of angle MOC, according to our diagram, is just x. And that's going to equal 180 degrees. Okay. Now, combining our like terms, we can come to there being 3x's plus 30 equals 180. And now we're going to solve this out. So I'm going to subtract 30 from each side. Gives me 3x equals 150. And to get it to single x, I'm going to divide both sides by 3. So x equals 50. So going back and recapping these pieces, what properties did we use? This is simply the definition of supplementary. Then we use substitution. In order to fill in those values, we combined like terms, which throughout these video lessons you'll see me abbreviate as simply CLT. Now, using our properties of equality to move from this line here to this line here, we got rid of that 30. Well, since it was addition, what we had done was subtraction. So I simply write on the side here, subtraction property of equality. Now, some people like to write that they subtract 30. I've also seen notation where people write S30, the S standing for subtraction property of equality, and then 30 as a reminder of what was subtracted. Okay, you'll see a lot of different notation for this, so just find the one that works for you. Then, in order to move from my 3x equals 150 to x equals 50, we use division property of equality, or if you want, we divided by 3. Both sets of notation are acceptable. All right, so we have all these properties when it comes to algebra. What equivalent systems do we get once we start working into geometry? Looking at our geometric properties here, there are quite a few less of them, but they do have equivalents in algebra. We have the reflexive property of congruence, symmetric property of congruence, and transitive property of congruence. And when we are looking at these, we do have them for both line segments and angles. So when I'm looking at my reflexive property of congruence, I have that line segment AB is congruent to line segment AB. Going with this in terms of angles, I could say that angle A is congruent to angle A. Basically, any item will be congruent to itself. Okay. Symmetric property, when I'm looking at line segments, symmetric property of equality says that if line segment AB is congruent to line segment CD, then line segment CD would have to be congruent to line segment AB. Similarly, with angles, if angle A is congruent to angle B, then angle B will be congruent to angle A. Simple back and forth between those concepts. When I get looking at transitive property, of course, as we saw with the properties of equality, this one is a little bit more involved. If line segment AB is congruent to line segment CD, and line segment CD is congruent to line segment EF, then that simply means that line segment AB is congruent to line segment EF. So just like with the algebraic property, I can simply skip over this middle linking piece and move from the first to the last. Okay. Then, with our angles, if angle A is congruent to angle B, and angle B is congruent to angle C, then we can simply say that angle A is congruent to angle C. And once again, we're just skipping over B as a middleman and going straight from the first to the last. Okay. So how do I really distinguish between the properties of equality and the properties of congruence? A lot of it comes down to just the symbols used. If you see an equal sign in between, we have a property of equality. If you see a congruent sign, we have a property of congruence. Okay. So all these properties will come into play as we go through and do proofs, which is a large portion of what our study of geometry is. It's a way of organizing information and using it to make a valid argument. So a proof is a convincing argument that uses deductive reasoning, remember this is logical reasoning, to show a relationship to be true. Sometimes in a diagram or in a situation, we are given limited information, but then from other things that we know, experiences we've had, in geometry, theorems or postulates that we've run across and worked with already, we can prove that other relationships also exist. This can be inside of a single shape or it can be between multiple shapes. Okay. And when we look at proofs, we really have three main types. A two-column proof is organized, just as it suggests, into two columns. On the left-hand side, we make statements. On the right-hand side, we give reasons. And the statements are a lot of times our algebraic work to solve for x. It is statements of congruence or equality. And on the right, the reasons are the names of those items or theorems or postulates that justify certain relationships being stated. A paragraph proof, as our next one, also like it sounds, is simply a paragraph. My common idea for this is what happens if you're working at home and taking a class, somebody else from that class sends you a message at night saying, hey, I need help with problem number 5. How would you go about explaining to them how to do problem 5? You'd have to, either by email or text message, write out a description of what's happening, and through that you might say, because of, in this case, let's say theorem 3.7. And then we go through and we give more explanation. And this is because of postulate 1.2. And we continue to go on until we've explained how to do the problem. Okay. Paragraph proofs take a little bit more time, I believe, to structure, but they read very nicely because it's just what you would do having a conversation. Now, a flow proof, the main ideas, the items that would come across as our statements, are given in bubbles. And either underneath them or sometimes in a catalog off to the side, we give justifications. And this is a way of organizing items that flow together. So this item makes us think of this item, which tells us this next piece. On a separate track, this opening thought leads to this thought, and then eventually those two come together to give us our final statement. Flow proofs are very handy if we have multiple tracks or trains of thought coming together to a single conclusion, whereas in a two-column proof, we would be blocking it out into sections and then hoping that people see the connections between the sections. So each one of these methods has its advantage. Each one also has a little bit of a disadvantage. The one you see most common is the two-column proof in mathematics. In many others, it comes out, many other disciplines of study, it comes out in the paragraph style. Okay. So let's take a look at one and see if we can put it together as we go. So given that the measure of angle 1 is equal to the measure of angle 3, prove that the measure of angle AEC is equal to the measure of angle DEB. Okay, and we're going to do this one in our two-column method. So I'm going to set up my two columns. On the left, I have my statements. And on the right, I have my reasons. And sorry for the roughness of the handwriting. Misplaced my writing tool. So when I do a proof, I always try and start with the given information. So up here we have given measure of angle 1 equals measure of angle 3. And my reason is simply that it was given. Okay. Next, we have this piece up here in our diagram. Here's angle 1, here's angle 3, but in between them we have this angle 2. And since I want to get to angle AEC, which includes both angles 1 and 2, and angle DEB, which also includes angle 2 but angle 3, I want to be sure to make the statement that the measure of angle 2 equals the measure of angle 2. And that is simply our reflexive property of equality. I'm going to put reflex equals as my shorthand. Now, I can put together that the measure of angle 1 plus the measure of angle 2 equals the measure of angle 2 plus the measure of angle 3. And that is simply the addition property of equality. I added the same thing to both sides of my original equal sign, so I still have an equivalent equation. Okay. Now, what is the measure of angle 1 plus the measure of angle 2? Well, in our diagram, that is that the measure of angle 1 plus the measure of angle 2, we're going to call that the measure of angle AEC. Okay. And then similarly, the measure of angle 2 plus the measure of angle 3 equals the measure of angle DEB. And for both of those, those are angle addition postulates. And same thing for this next line. Now we can get down to the measure of angle AEC equals the measure of angle DEB, that is using substitution. Okay, so using these properties of equality, I went from a given piece of information and other known facts in order to reach the conclusion that we wanted. Okay, so deductive reasoning tells us what we have, and our properties of equality in this case, or if we talked about congruence, properties of congruence in geometry, lead us to our final destination. Now, writing proofs takes a little bit of practice, so make sure you get a lot of practice on these, and if you get lost a little bit in the middle, just go back to what facts we know and where we want to be.